In this episode, we are going to solve three problems on the arrangement of capacitors. Let's start with our first example. Example 1. Two 6 microfarad capacitors are connected in series with one having a capacitance of 12 microfarad. Find the total equivalent circuit capacitance. And the B part says what capacitance must be added in series to obtain a capacitance of 1.2 farad. So let's look at how we will solve this problem. So first, two 6 microfarad capacitors are connected in series with a third capacitor of capacitance 12 microfarad, and we have to find the equivalent circuit capacitance. So first, for the two 6 microfarad, let's say our C1 is 6 microfarad, and there are two, so C2, the second one, is also 6 microfarad, and they are connected in series with the third one, so let's call that C3, which is also 12 microfarad, all in series. They are all in series. So with these three arrangements, let's find the circuit total or equivalent capacitance. So let's CT be the total equivalent capacitance. So we will call the equivalent capacitance as CT. And for series arrangement of capacitors, we have our one on the total or the equivalent. That will be 1 on CT is equal to 1 on C1 plus 1 on C2 up to 1 on the nth capacitance. So we have three of them. So we are going to get 1 on the total or equivalent to be, the first capacitance is 6. We are going to work in microfarad plus 1 on 6 microfarad plus the third one, 1 on 12 microfarad. Now, if you continue to punch all this, this is going to give you 1 on the total, which is equal to 5 on 12 microfarad. And this, if you reciprocate your answer, then the equivalent capacitance is going to be 12 on 5 microfarad, which is 2.4 microfarad. Are you okay? So now this is the circuit equivalent capacitance from the three capacitors arranged in series. Now the B part, what capacitance must be added in series to obtain a capacitance of 1.2? Now from the first part, we are now having a capacitance of 2.4, and the question is, how do we obtain a capacitance of 1.2? By adding a third or a fourth capacitor. What is the capacitance of that capacitor to give us the total or equivalent capacitance as 1.2? Is that clear? So here we are going to solve it this way. So also we are going to obey the same capacitance. C1 is still 6 microfarad. C2 is also 6 microfarad. We have our C3 to be still 12 microfarad. Then C4, the fourth capacitor to be added in order to obtain that capacitance, is unknown. So let's call it X microfarad. Are we okay? So now, and we want to obtain a total capacitance of 1.2 microfarad. Are you okay? So now let's find the value of X for the fourth capacitor. Remember, they are all in series. So meaning our 1 on CT should be equal to 1 on C1 plus 1 on C2 plus 1 on C3 plus 1 on C4. So when we put in the value 1 on, the total we are looking at is 1.2 microfarad, which should be equal to C1, which is 1 on. We still have our 6 microfarad plus 1 on another 6 microfarad plus C3, which is 1 on 12 microfarad plus C4, 1 on X microfarad. So from this, we are going to make X the subject. Are you okay? So with this, what do we do? If you bring all these parts to the other side of the equation, you are going to get what we have as 1 on X should be equal to 5 on 12 microfarad. Are you okay? And this, when you make X the subject, your X is going to be 2.4 microfarad. Is that clear? So this means that if we add another capacitor of capacitance 2.4 to the first one, which gave us 2.4 microfarad, then our capacitance is going to reduce to 1.2 microfarad. Are you okay? So this is the first example, very examinable. So let's look at the second one. Find the capacitance to be connected in series with a 10 microfarad capacitor for the equivalent capacitance to be 6 microfarad. Very simple. So here we are given some capacitance, so which is C1, and that is 10 microfarad. And we also have the equivalent capacitance, which is C what? Equivalent, the total, to be 6 microfarad. Now we are looking for a second capacitor which will help us, if connected in series with the 10 microfarad, will give us this total capacitance. So another second capacitor, which is C2, we don't know. So let's call it X microfarad. Are we okay? And in series, this is going to help us to get it, which we know that 1 on our CT plus 1 C1 plus 1 on C2 should give us the answer. We have the CT, which is the total, as 6 microfarad. We have C1 as 10 microfarad plus 1 on X microfarad. Is that clear? So here we are going to have 1 on X microfarad, which is equal to 1 on 6 microfarad minus 1 on 10 microfarad. And with this, we are going to get our 1 on X microfarad to be equal to 1 on 15 microfarad. And this indicates that our X is equal to 15 microfarad. Are we okay? So meaning the capacitors to be connected in series with the 10 microfarad capacitor to give us equivalence of 6 microfarad is 15. Are we okay? So meaning if you punch 1 on CT, which is equal to 1 on 10 plus 1 on 15, then your CT should give you what? 6 microfarad. If they are all in microfarad. Are we okay? So this is very simple. Let's look at the third one, which is quite interesting. We will need a lot of time to analyze our third one. Now, example 3. Please pay attention to this example. For the arrangement shown in the figure, find A, the equivalent circuit capacitance. So you can see that we have combined arrangement. both parallel and series arrangement of capacitors. So we are to find the overall capacitance in the circuit. And the B part is the voltage across the 4.5 microfarad capacitor. So we'll check the voltage across one of the 4.5 microfarad capacitor. Are you okay? So let's look at how we can solve this. In order to get this right, I will prefer to label the circuit. So let me call this part as the A part, and I'll call here as the B part. Are you okay? So now at the A part, all the three capacitors are in series, and at the B part, the two capacitors are also in series, but A and B are parallel to each other. Are you okay? So our analysis can be made. So let's look at the solution. From the A part, from the A part, which is a series what? Connection. So we have series connection and we have three of the capacitors. So I will let CA be the equivalent capacitance at the A part. Are we okay? So I'm letting the total capacitance across the A part for the three capacitors to be called CA, and they are in series. So my 1 on CA for the A part is going to be 1 on 4.5. Remember, they are all in microfarad, plus 1 on 4.5 plus 1 on 4.5. This is going to give us 1 on CA to be equal to 2 on 3 microfarad, and it implies that our CA is going to be 3 on 2, which is 1.5 microfarad. So meaning the total capacitance across the A part is 1.5 microfarad for the three 4.5 capacitors. Are we okay? So now let's look at the B part. From the B part, which is also series connection. Now let CB be the equivalent. Please always define your parameters. Equivalent capacitance. Are we okay? So at the B part, we are going to have the CB for the total capacitance. So that is also in series. So my 1 on CB is also going to be 1 on, each capacitor is 1 microfarad. So 1 plus 1 on 1. And this is very simple. It implies that my 1 on CB is going to give me what? 2, which implies that CB is actually 1 on 2, which is 0.5 microfarad. Is that clear? So now let's look at the diagram, how it is reduced to. So now we have the A part as this capacitor, which is the A part now. And at the B part, we have also this equivalent capacitance. And still with this three parts, we still have our diagram. So this is the voltage source. All right. So this is the diagram that we have. So the A part gave us 1.5 microfarad. The B part gave us 0.5 microfarad. We still have our 3 microfarad and the voltage as 500 volts. Now, when we look at the A part and the B part, they are also parallel to each other. So now we can find the parallel arrangement for A and B, the equivalent capacitance. So you can draw the diagram. We move to the next page. Now, finding the equivalent capacitance for A and B, which are parallel. So I will let CAB be the equivalent capacitance for the parallel arrangements. The parallel arrangement of A and B. Now, for parallel arrangement, then our CAB, which is the equivalent, is just the summation of the A parts, CA plus CB. So that is going to give us 1.5 microfarad plus 0.5 microfarad. And this is leading us to 2 microfarad. So that is for CAB, the parallel arrangement. So now we can see that this 2 microfarad, which is CAB, is in series with the 3 microfarad, and that will be the total equivalent. So now let's find the total equivalent capacitance, and that is also going to be CT, and our CT comprises of the 2 microfarad and the 3 microfarad, which are also in series with each other, meaning our 1 on CT, which is the final equivalent, is going to be 1 on 2 microfarad plus 1 on 3 microfarad. And how are we going to get this? When we punch this, our CT is going to be 1.2 microfarad. Therefore, the A part, our total circuit equivalent capacitance from the arrangement is 1.2 microfarad. Are we okay? So now the B part says we should find the voltage across. You can go back and check the diagram. We must find the voltage across a 4.5 microfarad capacitor. Are we okay? So now let's look at how we can get it. Let's draw the diagram again so that we can see that. So this is our diagram, and we are to find the voltage across the 4.5 microfarad capacitor. So what do we do now? It is very simple. We will have to calculate the total charge being produced by the voltage source. Are we okay? Or the total charge being distributed in the entire circuit, because we have, so the B part, we have this formula: the total capacitance of the circuit is equal to charge, or the total charge on the total voltage. So if we want to find the charge in the circuit, that is going to be the total capacitance, which is now 1.2 microfarad from the first part to the power -6, and the total voltage is 500 volts. So meaning the total charge in the circuit is going to be 6 to the power -4 coulomb. Are you okay? So this is the charge being produced throughout the circuit. Is that right? Now, we will have to find, as the charge is approaching or moving through the circuit, you have to find the voltage across the 3 microfarad capacitor. Are you okay? So let's imagine this is current moving. There will be some drop at the 3 microfarad capacitor. The same thing happens to what? The charge. So let's look at the voltage at the 3. So now, voltage at the 3 microfarad capacitor. That is going to be from the same equation, C is equal to Q on V. Then we can say that our voltage across the 3 microfarad is going to be, remember, through the 3 microfarad, all the charge is passing through. Are you okay? Because it is in series with the voltage source. It is at the A and B points where we are going to get a split of charge. So now, to get the voltage, we are going to use all the charge, which is 6 to the power -4 on the capacitance we are talking about, which is 3 micro to the power -6. And with this, we are going to get 200 volts. So meaning out of the 500 volts, 200 is dropping at the 3 microfarad capacitor. So by logic, what do we have? We now have 300 volts to work with. Are we okay? We now have 300 to consider. And what do we know about capacitors in parallel? We have the same voltage across them. Is that true? Yes, the same voltage across them. So meaning the voltage across the 3 resistors or the 3 capacitors at A should be the same as the voltage at B. So now let's look at how we can get each of the voltage across the 4.5. So now we have 300 volts to work with. Therefore, by our observation, 300 volts is now for the parallel arrangement. Is now for the parallel what? Arrangement. Is that true? So meaning the total voltage across these 3 is what? 300 volts, and that across these 2 is also 300 volts because they are in parallel and the same voltage applies. Are you good? So now let's look at the charge flowing through the A part. The charge flowing through the A part. We now know the voltage of it. So let's try to find the charge. So now, out of the total charge, which is the 6 to the power -4 coulombs, we want to find the amount flowing through the A part. So that is also going to be charge at the A section is going to be the capacitance at the A section, which is the equivalent capacitance C, multiplying the total voltage at the A section. And we know that at the A section, the total capacitance was 1.5 microfarad, so which is to the power -6. And our voltage, we know it is 300. Is that true? So meaning at the A section, the charge is 4.5 to the power -4 coulomb. So each 4.5 microfarad capacitor at the A section is experiencing a charge of 4.5 to the power -4 coulomb. Therefore, we can use the formula voltage at 4.5 microfarad is going to be the charge passing through it over its capacitance. And that is going to be the charge we know now is 4.5 through each of the 4 microfarad. And the capacitance we want to find is also 4.5 to the power -6. And this is going to give us 100 volts. Are you okay? It is very simple. If this was to be an objective question, we could just look at it and get the answer right, because now we know that 200 is dropping at the 3, meaning we have 300 more, and the 300 more, A part has what? Total of 300. B part has total of what? 300. Meaning out of the 300, they are also going to be distributed among 3 capacitors of the same capacitance, meaning it is going to be 100 across each. The same thing happens to the B part. We have 300 voltage across the 2. Each of them is 100 or 1 microfarad. So meaning they are going to divide the voltage. So if you calculate the voltage across each of the 1, you are going to get 150 volts. You can check that one out. So thank you for watching this episode. These examples or problems are highly examinable. So pay attention, go through the video again and get it right. Drop your comments, subscribe to the channel, and let's look at what we will have in the next episode. Thank you.